hello. My name is Sean Vanderbach. I'm a data engineer at Skills. Today we're going to be talking about large volume data replication from MySQL to Snowflake. So it's kind of a rather specific use case, but kind of goes to show some of the tricks that you can utilize with StreamSets to get large volume data ingestion. So quick intro for me. I graduated college about 2.5 years ago, and then joined Skills. I've been there ever since. So a little bit more about this talk. We're going to quickly go over kind of our journey through using StreamSets from the original implementation that we used to how we improved upon that about a year after we originally implemented it. And then we'll talk a little bit about Kubernetes and the deployment of StreamSets on Kubernetes. Yeah, let's get into it. So quickly to just recap the goals, demonstrate large volume data replication from MySQL to Snowflake, specifically to kind of meet some stricter SLA times. And then we're going to touch on the deployment of SDCs on Kubernetes. So the agenda for that is going to be, we're going to cover the use case, we'll talk about the original implementation, the problems that we saw with our original implementation, kind of what we wanted to fix about it. And then we're going to go into kind of that solution and what the results of that we saw, as well as some of the monitoring and alerting we use to make sure that end-to-end is covered and our system is healthy. Just going to move on from there. So first part is our journey. Our use case for what we wanted to do was we have multiple MySQL read replicas. We wanted to get the data from those multiple databases into Snowflake. We had an old software that we used for this that was basically going to be gotten rid of completely. It discontinued when I joined. So we had about 2 months to basically swap over to StreamSets and implement everything, which was a pretty tight timeline for us. And then another goal that we wanted to do besides just getting all this data from different databases, to kind of put it in perspective, it's a little over 100 tables that we wanted to sync. We wanted to also get everything synced over within a specified SLA. At the time, we just wanted to get it from our current every 60 minutes that we were syncing to around less than 30. You'll see later we've gotten it even to be less than 10. And we probably could even go further down than that if we wanted to. It just turns into kind of a cost problem for us. As you can see, minimizing costs is kind of always a priority. So looking at our original design here, we can see basically 5 key steps here of our pipeline. So to give a little bit of background, we actually have about 4 pipelines that we use mainly, but 2 main fragments that we use. And so we have basically 2 pipelines per fragment that we have. The primary one is just to do the sync, the replication from MySQL to Snowflake. And then the second one that we have that uses the same fragment would be what we call a restream process. So if we get error records, we write those to S3, and we want to be able to get those records into the destination tables in Snowflake without interrupting the flow of data. We don't want to stop the pipeline because there was an error. We want to just process those records later on. So the big components here is the MySQL binary log consumer. We're just going to read through the bin logs on the database side of things in MySQL and know the changes of data that need to be done and written to Snowflake. So this is all CDC based. And then the second step that we have here is we want to set some metadata as the header attributes. So some example of these that comes from the MySQL binary log consumer would be something like the gtid offset if you have gtid enabled on your MySQL database. Or if in some case we actually don't have gtid enabled, we're kind of mixed right now. We have some gtid enabled, some not. So we just use the binary log offset for that. And we want to map some of those metadata to the fields. A key one that we use is actually basically just the time.now of when it's being processed. We have like a metadata timestamp of when the current records is being sent through the pipeline. And that is a key value that we use for merging the data later on. And that's how we know whether or not a record is older or newer than a previous record, especially when restreaming aired records. And I'll kind of cover that problem a little bit later on. And then we do some basic transformations. Most of these transformations are actually not really needed for us. We do most of our transformations downstream. The transformations that are current in our pipelines right now are actually originally designed to swap over from what we were on before to StreamSets. There were just some issues that we were having with typed data that we just needed to fix, and we haven't gone through and stripped all that out yet. So it's more of just for compatibility reasons from our old to our new. And then for the Snowflake destination, this is a big one we're going to be talking about in terms of the solution to our problems, because originally we had it set up for merging. So there's like this setting within the processor for, do you want it to do merge or just a basic like copy into? And originally we had it set up for merge, but that's where our problems started coming from.
Does it handle all the nulls and anything before it goes to the Snowflake?
Does it handle the nulls?
Yeah, anything that might error out the transformation.
Yeah, so in our transformations, one of the things was the StreamSets MySQL binary log consumer doesn't like handling tiny ints or bit ones, especially the null values of that. So we actually have a groovy script that runs on it and takes care of all those nulls and converts them to integers or booleans or whatever we have. So moving on here a little bit. So this is once again basically just a diagram of what was in the previous and what everything's doing. So we're starting out with our MySQL. We have whatever schemas and tables we have as part of the database, and then we're entering our our environment in Kubernetes. So everything's internal to us at that point, where the data is being written out to S3, or it's being staged in S3 for the Snowflake processor to essentially merge. But the biggest issue here is from the data collector side, it goes from the data collector, it stages in S3, and then the data collector essentially says, okay, merge the data. And then it waits for the merge to complete before telling StreamSets that the data has stopped merging or finished merging, and you can go on to the next step. So that's where we start to see the problem, is that it's waiting. So it's a single-threaded pipeline. It starts, and then we have to wait for the merge before we can start doing everything else again. But as you can kind of imagine the whole process from the previous slide, these processes here also take time to run. So in our minds, we're thinking, okay, how do we get it so we can continuously run these processes without having to wait for the merge at the end? Because otherwise this is wasted time. And that's where we started getting into our solution a little bit. Once again, covering the problems here, the single-threaded aspect of the MySQL binary log was locking all processing time while waiting for the merges. It also made disaster recovery options limited to vertical scaling. So you can kind of see from the graphs down here, we would occasionally have issues where we'd start getting a ton of data, or like peak data traffic times for our systems, and StreamSets wasn't able to keep up with it, like using the base pipeline that we had before. And the only option that we had to fix that was basically going into Snowflake and vertically scaling up the warehouses. So going from an XL to a 2XL or a 3XL, which ends up costing more money. Also, I mean, it's waking up engineers at night. And then the other issue was, with our old system, the merge overlaps old records without accounting for timestamps. So whenever we ran the restreams, a quick example of this would be, let's say you have at T0, or T equals 0, you have record A come in. And at T equals 1, you have an update to record A. And at T equals 2, there's another record, basically another update to the record A. Let's say that at the T0 version of record A aired out. So at T1, we get the updated record, and then let's say we're restreamed at T equals 2. The original record that should have been from T0 is now overriding T1. which is bad, because, I mean, that's the wrong data. That's the old data that we have. But with our new system, we can actually compare the timestamps to each other for the merges that we're controlling, because with our solution, we control the merge queries as opposed to StreamSets handling them. We can actually compare the timestamp ourselves and make sure that the records that we're restreaming aren't overlapping newer records that possibly could have been added to the data while they were sitting in S3 still, while their records were sitting in S3. So that's where we get into kind of leveraging the Snowflake compute for merges. So we start out with basically the exact same setup, except for we end up using the copy into down here for the Snowflake destination processor. So we just uncheck this, and that defaults all the statements to be copy into queries as opposed to the merge queries that were auto-generated by StreamSets before based on whatever we had passed in. And so what this is doing is it's letting us copy all the data to some like staging table in Snowflake. So we're staging everything in S3, and then it's copying directly into a Snowflake table, like a intermediate table. And then from there, we're going to be merging all the data from that intermediate table into our destination table. So we're completely decoupling the merge aspect that we had to wait for on StreamSets, and we're taking that all and putting it on Snowflake. That way, StreamSets is just in charge of running the very quick copy into statements. It runs a lot faster than waiting on the merges. There's no lock for the merges. And we basically just have data going to Snowflake all the time, which is great. So you see the little difference here is that once, all we have in the Kubernetes is basically the data being staged to S3 and then being appended to our changelog table. So all this can just keep running constantly, and then we can set up a set of Snowflake tasks, or you can use any other orchestrator you want to basically run the merge queries on a cadence that'll merge from the changelog table to the target table. So once again, we're basically all this right here just gets to run constantly, and then we occasionally run the merges, which are the longer taking queries. Basically just only on Snowflake and not as part of StreamSets. It's also effective because, I mean, we can control the cadence of these merges as we want. So if you need to, save more money with Snowflake, you can, run them on like 30-minute intervals as opposed to 10-minute intervals, or if you need the data more available, you can run it, on a smaller interval. You just gotta worry about how long those merge queries actually take. Which, if you're running it on more data, scales kind of better than running a ton of merge queries on small batches of data. So the impact that we saw from this was that data can be continuously dumped into the changelog while the merges are occurring separately. And then we have more disaster recovery options because we actually have some horizontal scaling that can come into play. Because we're running all the merges independently in Snowflake, those are more queries running, but they're going to be a little bit less intense. So we can scale the warehouse out horizontally instead of just vertically, which gives us a little bit more play in what we're doing. Also, in terms of disaster recovery options, we can actually run manual runs of those merge queries if we need to. Like, let's say the queries are timing out on the automation side, because there's a lot of data and something went wrong. We have some time to kind of play with the data, and we can actually run manual merges on our end if we need to fix things, as opposed to basically shutting down the pipelines and having to do that. We can just do it like disconnected from everything that is already running. Additionally, we did see a 50% cost savings from using this method over the previous one, and a lot of that comes from the fact that the copy intos are pretty cheap, even though those warehouses are running all the time. They can be very small. And then the merges occurring, we're doing it on a cadence as opposed to with StreamSets, it was just basically turning on the warehouse and running it whenever it got to that end stage, which when you're running multiple pipelines could mean that that warehouse is on 24/7. But if we can control the cadence of the merges, then we can say, okay, run all the merges every 30 minutes, and that warehouse is only going to be active for like a 5 to whatever minute period during that 30 minutes. So you could essentially have all your data being synced like twice in an hour or something, only using the warehouse for 10 minutes, as opposed to the warehouse being live 24/7, or up for the whole 60 minutes. And then the ability to handle error records without disrupting system uptime. So that's what I mentioned before in terms of when we have this timestamp value that we are passing, and with these merges that we're customizing as opposed to StreamSets just automatically creating those merge queries, we can define this timestamp to tell the difference between old and new records when we're restreaming these error records out, as opposed to basically just saying, okay, whatever's coming through the pipeline is the newest record and overwrite the old one, which gives us data integrity issues. And then we've also just, ever since swapping over, have had a general reduced number of incidents that we've had, mostly due to the fact that we're able to handle these high traffic periods that we were having before that were causing us issues. So some improvements that can still be made to this that we haven't implemented. One is using stream tables on the Snowflake side of things. That way that we're only performing merges on data that's new coming into Snowflake, as opposed to right now it's just basically a changelog table of a ton of records where we have that metadata timestamp to determine the difference, or to determine how old records are. So basically we keep like 24 hours worth of data right now, and we do a merge on about 2 hours of that data on whatever cadence we have. But with the stream tables, we could just say, okay, let's just keep the changelog as an ongoing record of all the CDC, all the changing data that's occurring, and then only merge over what is new. And we don't have to like play with those time windows like we are now.
Can you not check that what is changed at the source, like at MySQL, instead of breaking it to go on the original pipeline?
Yeah, so we do take the change data from MySQL. The problem is kind of how we handle things is that change log table we have isn't really just the change data. It's like, it'll be like, you know, all the updates or the inserts, all the records that are coming from MySQL, all that, like, I guess, change data, but it might not be coming in at the right time. So for like the error records, we stream it into that same table. So we need to be able to resolve differences in that table. So it's not really the data that's changed, it's just kind of a table full of changes that we then merge over. I don't know if that makes sense, hopefully. But yeah, it's kind of the same, and I mean, we could implement something, I guess, on our side to like flag what has been, you know, added to the table or not. But I mean, when Snowflake has something that's kind of already built in to do that, that would probably be easier for us to use. And then a second improvement we could make would be using snowpipes. Like you can use snowpipes with a copy into as part of the StreamSets processor already, which is great. We haven't implemented it yet, but I mean that could just give further cost optimization further cost optimizations because of the fact that it's only going to use the resources it needs to do those copy intos as opposed to whatever we just have the warehouse set as.
And how are you doing the horizontal scaling? Are you using Kubernetes for that?
So the horizontal scaling would be on the Snowflake warehouse side. So just the cluster size of that warehouse. And that would just be done, I mean, either manually or we have some Terraform that manages a lot of our warehouses as well that we can just change the code. It's not like dynamic scaling, it's pretty much only scaling if we have incidents and we need to fix things.
Yeah, I just want to see what is the purpose of the Kubernetes if you're not using it.
Oh, so on the Kubernetes side, it's more of, that's just where a lot of our infrastructure lies, and that's for the SDCs themselves as opposed to the compute for the queries. So it allows us to manage the infrastructure of the SDCs a lot better within Kubernetes. And I guess, I mean, we could use other methods as well. It just fit with what our current infrastructure already had. And we'll discuss the Kubernetes aspect a little bit more later on.
So are you managing the data collectors in the Kubernetes as we have exactly this many running, we keep those running, like treating them as the same as you would a server? Or are you actually scaling it up and down?
So it doesn't scale up and down for the SDCs. We say like, okay, here's the deployment for, I guess, SDC one that has 2 cores or something. And Kubernetes is just making sure that that SDC is always up. So it has the availability aspect to it, which I guess is one of the benefits of Kubernetes. But it's not scaling on the Kubernetes side. Is that good? So a little bit of monitoring and alerting that we have kind of set up throughout this is before we could just basically track the time on the destination tables at the end, the lag there to make sure that data was getting there. But when we start introducing more components of the changelog table versus the destination table, and we want to know where the problems are lying, we start adding a little bit more metrics in. And then we just have some additional ones on top of that, like failed merges and the merge times, so how long the merge queries are taking. So if we have a cadence of, let's say, 10 minutes, for example, on the merge queries, those merge queries need to finish running within 10 minutes, or else it's going to interfere with the next runs. So we normally have timeout set of like, okay, if the cadence is 10, the warehouse is going to time out the query after 9 minutes or something like that. And this just helps us keep track of, are our merge times getting too close to that line that we need to do something about, scaling up the warehouse or something else. And then on the StreamSets built-in subscription side, we actually use that to track our job status and our SDC status. So is an SDC down, or did a job stop running for some reason? Which are nice things to know, because then your data is not streaming. So ultimately, though, the lag monitors are kind of the most important, because if a table is not being updated in the time that we expect it to, something's wrong. So that's kind of our overarching one. And then everything else kind of just exists for more details as to what is going wrong in the system. So the chapter 2 here, deployment of Kubernetes, is, I'm pretty sure it's actually just like a slide. Yeah, it is. So we manage all of the SDC configuration within GitHub. We have the provisioning agents, which I believe we have 1 per environment in Kubernetes, because we have our 3 environments kind of, defined as different environments within Kubernetes. And then we have like some JMX values that we pass to track some of the metrics that normally come from the SDCs, but we want to expose those. We have like a sidecar container basically on the SDCs that helps ship the JMX metrics out. And then for the SDC itself, there's some like SDC properties. Some of those might be like the runner thread count, which kind of controls a little bit like how many of the jobs can run within the pipeline, the credentials that we need for the SDCs to be running, and then some of our logging properties as well. And then we control all of our SDCs as specific YAML files within GitHub. And I'll go over a little bit about our structure for deployment as well, since I think we're doing pretty good on time. But that's kind of also an interesting aspect of, I guess, our infrastructure and how we have things defined. And then, basically we just deploy the SDCs utilizing the Python SDK, and it's kind of a rolling deployment. So it'll basically look for all the SDCs, check the number of pipelines that are active, and then it'll start systematically like restarting them, but waiting for them to come up again before going on to the next. That way we're not restarting all at once and the jobs aren't running. And then between every restart of the SDCs, it double checks that all the jobs are still running. So does the job count from the beginning match what's at the end? And that's just to give us kind of a secondary check that nothing stopped working in the meantime. So I have this as questions, but I'm actually going to go to the appendix here where I have a little bit more of our deployment stuff defined. So this is actually an image of what I was talking about with the error records before. I mean, basically we can just see from StreamSets, if a record errors out, then we'll get an alert, and that error record will be sent just to S3 and stored. And then an engineer ends up getting paged from this because we want the data to be available. And they go in, and we have our separate pipeline that I was talking about earlier for these restreams, which is basically just swapping out the MySQL bin log consumer for the AWS S3 consumer. And then it uses the same fragment for the rest of the processing. So basically it's just picking up the data from somewhere else, and then it's going to be dumping it into the change log, and the merge will actually handle everything else downstream. So for the revised version, the difference between that and the original version is just that record timestamp that we're looking at. We also have, so right now we don't have any proper, I guess, automated CI/CD that occurs for whenever we update pipelines. It deploys it, across our SDCs and updates the jobs and all that. But we do have some SDK scripts that we use for all of our deployments, so we're not just doing everything manually. And so we have stuff like job creation, job redeployments, we have SDC redeploys, SDC restarts, basically just some scripts that we can run to do different things if we need that done without having to manually intervene every time and run all this stuff ourselves. So kind of the structure we use for job deployments, not necessarily job creations here, but we have this configuration file that we have set up within, I guess, our GitHub repository, and our script basically reads from that configuration file and then runs a ton of the SDK stuff to deploy jobs based off of that configuration file. So the configuration file is just a JSON with all the runtime parameters defined for a specific job we want. So we have our two pipelines. We say, okay, for this pipeline, here's the JSON that we have. Basically create a job for every job that we have defined within the configuration file, and it just takes all those runtime parameters and populates, 15 or 16 jobs that it runs. And that makes things a little easy for us. And then on the Snowflake side of things, I want to quickly talk about, I guess, this aspect of things, the Snowflake tasks. So we have a lot of our Snowflake resources actually defined through Terraform, using a Terraform provider through Snowflake Labs. And for these tasks specifically, we have one procedure that we use. So the procedure is defining our custom merge query that we want to utilize. And then it's parameterized to be based off of, I guess, these parameters that we're passing in for a specific task. So for the 100+ tables that we actually have a file that uses the Terraform provider to systematically generate those like 100+ tasks. So there's one task per table with different parameters that are being passed to this singular procedure in Snowflake. So we can basically control the merges of every table individually, even if we don't have like each specific table being managed on StreamSets itself. Because we only have, for like 100+ tables, we only have like 20 jobs defined in StreamSets for that. And that's because we group a lot of the tables together and just run their records through together with each other. Because I mean, there's separation of that. With the MySQL bin log, you can define like a subset of tables, and it'll just like batch out records and put them in different areas using the metadata.